This is part 3 of the episode on how to write a good NFT smart contract. It focuses on NFT smart contract deployment and on the minting stage, which is the most critical stage for any NFT project. Let's go. The next stage is deploying the smart contract. The first thing that you need to do is to come up with a sensible deployment strategy that is safe and future-proof. So if the deployment tools need access to your private keys or need to store those private keys anywhere on your computer, then you have to make sure that those private keys cannot be accessed by anyone, or even that you use it once and for a very short time, and then transfer ownership as soon as you deploy the smart contract. Using a hardware wallet is also a sensible thing to do. So deploying a contract from a burner wallet means that deployment of the contract will be the only transaction that wallet has ever performed, or maybe one of two transactions, so deployment and then transferring ownership. And that's it. Then even if someone gets access to that burner wallet, then it's useless. You also need to know when to deploy your project. You need to be aware of gas prices. This is the historical chart of gas prices. There are more quiet periods, there are more busy periods, and this is the gas tracker with the current gas price. So while knowing the historical data, you also need to be aware of what is upcoming in terms of, for example, different NFT projects that may be popular and that may influence the gas price significantly if it's a project that many people are waiting for. And NFT calendar is a good resource to check what is upcoming, who is minting and when, and then plan accordingly to avoid other potentially popular projects to mint at around the same time. The next thing that you need to do after deploying the contract is to verify the contract on Etherscan. If your contract is not verified, probably nobody will trust your contract or will know what is going on inside the contract. So it's a step that you have to do, and there are tools for you to make it easier. You can either do it manually through Etherscan, which is tedious and not as easy to do, or you can use something like a Hardhat Etherscan plugin for Hardhat, which lets you automate the whole process. With this plugin, it's as easy as identifying the network, for example, mainnet, then providing the deployed contract address and a few constructor arguments that you have in the smart contract. That's it. But also, before deploying to mainnet, deploy to a testnet, test on a real marketplace. So there's an OpenSea on testnet. You can see how your collection will look on OpenSea by going to a testnet on OpenSea. You need to verify all the scenarios when you deploy. So you need to verify how minting out works. You need to verify how your NFTs are being displayed on OpenSea or other marketplaces, and if they work properly, if all the attributes are being displayed properly. But also at the same time, when you check everything on testnet, make sure to not inadvertently reveal the metadata and rarity info, because there are bots or people looking for test deployments on testnet to try and see the metadata so that they can take advantage of that when minting on mainnet. The big and important category, which is minting, a big part or even a majority of a smart contract logic, depending on the contract of course, is reserved for minting. First, it's a good idea to have a separate minting contract. So minting logic is, first of all, a common source of errors. And if something goes wrong, during the minting process, you do not want those potential errors to be in the contract forever. That might be taken advantage of in the future. And if you have a minting contract separate, then your token contract is much more simple and much easier to maintain and fewer opportunities for errors. Now for some very specific tips and tricks more around code readability and for making the code easier to read and maintain. First is fixed pragma. So do not do pragma solidity 0.8.7 or later when you set the compiler yourself. So if you control the whole process from the very beginning when you write the smart contract to the deployment, then you do not need to go like 0.8 or 7 or later, because you know when you're going to deploy and which version you will want to deploy with. So make sure to give the specific version instead of doing something X or more. Next, no magic numbers, no unexplained context in code. Everything needs to be self-explanatory. Everything needs to be clear. Nothing should be ambiguous. It's better to have constant variables that have long variable names than to have something that you might not be sure about what it means a month from now. Also, take advantage of readability keywords. Instead of going for like thousands of seconds, go for 1 day, for example. Instead of going 1 and then a bunch of zeros, make use of underscores, which is the same but much easier to use, read, and understand. Same goes for ether. So instead of having like 1 and 18 zeros, you don't need to count all the zeros. Just use ether's utils parse ether and then give the number of ether. So 1, 0.1 or whatever else, instead of counting the numbers, counting the zeros, and potentially making a mistake and then having something like 10 times more, 10 times less, which is disastrous. Require messages are helpful in understanding what that requirement is and what it needs to say. So instead of having just the require statement like this, have the require statement and the message what needs to happen in this require statement. Mentioned briefly previously, variable names, function names, or comments. Everything should be descriptive and accurate. So mapping 3 or data are very bad as variable names. Those need to be precise, accurate, and descriptive. So instead of data, have something that might even be like 3, 4, or 5 words, but that's very clear and you know what it does, rather than having data. Same goes for the comments. Have the comments tell what the function or the variable does, what it is, and if it's outdated, it's better to have nothing than to have an outdated or misleading comment. Unused variables are bad not just for readability and for understanding the contract, but also for gas savings and deployment cost. An important aspect of minting is metadata and media files, and those need to be stored safely and in the storage options that make sense. More on storage options in the previous episode, what technology to deploy NFT, but also don't share the URLs of your metadata files and media files, and same as discussed previously, be careful when launching to testnets so that you do not leak the metadata before minting on mainnet. Other aspects to keep in mind when minting is to optimize the storage, to limit the supply, and to protect against the bots. So one of the trivial and not necessarily effective ways to protect against the bots is to limit the mints per wallet, but the whole subject is actually much more nuanced and complicated than that, and this is what I'll focus on next. So preventing NFT sniping. It's not easy to prevent NFT sniping, And there are a couple problems with it. Problem one is revealing your token metadata. So when you reveal your token metadata, then it's all public, all on blockchain, all can be read by anybody. So even if you verify your contract just before minting begins, so that there is less time to have a look at the contract, that actually favors the NFT snipers and bots because they can do it more effective and faster than all the other users. You can always reveal the metadata only after all the tokens have been minted, but then there are two additional problems with it. First, what if the minting takes a long time, like days or weeks? Everybody needs to wait until everything is minted out. And what if it doesn't mint out for a month even? And second problem is that there is a disconnect between minting and actually seeing what you have minted. The anticipation is the largest at the moment of minting, but you do not get that reveal. You do not get that excitement for hours, days, or weeks, or even longer. Potential problem number two with NFT sniping is when you mint tokens in a deterministic order. This allows the snipers to check the order of minting, to see what mints when, and to try and establish which next token will be the rare one, and try to snipe at the right time to get that rare token. But then again, there are a few additional problems out of this problem. The first one is that Ethereum does not have a built-in random number generator because everything is deterministic. You can use a few pseudo-random things like block difficulty or timestamp, but it's all visible in the smart contract what you're using, and it's relatively easy for the snipers to calculate that and for the number to not be truly random. The way to solve this problem can be to use the oracles that have real random numbers, which make things more difficult is that you need to call another smart contract, the oracle, which also costs you. But then there is another problem with that. So even if you have a fully random number and it's not possible to predict what mints next in terms of rarity, will it be valuable or will it be common? The way to get around it is to create a contract that will, in essence, start minting, have a look inside of what is being minted and what is the rarity of that NFT, and if the rarity is not rare enough, then revert that and actually do not finish the minting transaction. And this is an example of such a contract that was built for minting MIBITs. The way it works is that it starts the minting process, the minting function, and then it checks the token ID. And it checks if it's a rare MIBIT or not. And if it's not, then it reverts the function and actually does not finish the minting process. This is the logic of the code that was used to snipe rare MIBITs. And it did cost a quite significant amount of gas for each peeking into the function of the minting process. And it was performed, I don't remember, maybe 100 or 200 times to check. And each time the gas was paid. But as a result, this contract was able to purchase one or a few rare MIBITs that were sold at a much higher price than the total that was paid for the gas. And there is no easy way to get around this and to solve this problem. You can try doing different things, but it all comes at a cost to the buyer, be it a financial cost or a cost of experience. This item, adding support for gasless listing on OpenSea, is something that is outdated at the moment because OpenSea introduced a new smart contract and a new marketplace. But this shows how the smart contracts are being built or need to be built with the future in mind. So previously, for example, you might or might not set the set approval function, which let the users mint on OpenSea without adding an additional transaction to allow you to mint on OpenSea. So in effect, you only had to do one transaction instead of one approval transaction and then one minting transaction. And that function was optional. You didn't have to have it in the smart contract, but when you had it, it was for your users to pay less when minting. So you needed to think ahead of what can be done, what will be done, and how your users can benefit. At the moment, it's already outdated and this function does nothing because there is no need for it. But that shows how you need to build your smart contracts. You need to anticipate what happens now and what might happen in the future. Avoid reentrancy bugs was mentioned already a couple times. The rule of thumb here is do not update the state of your smart contract after making any kind of transfer. First, you need to update the state and then send the transfer so that even if that transfer then re-enters, it's already too late because everything that needs to be done is already done. This one is for readability and for understanding what the contract and the functions do. And this is a great example from a Moonbirds contract where it explains what the function does and also why it does what it does and what was the reason for the function to work this way. Accepting non-ETH payments and, more important, enabling non-ETH withdrawals is important when, for example, your smart contract gets some ERC20 tokens either sent to it or just transferred because it's a publicly available contract. If you do not have a function to withdraw those tokens, then those tokens will be forever sitting in that smart contract without any possible way to cash out and to withdraw. You need to explicitly write that function to be able to do that. Use new Solidity error types. It's a convenient and gas-efficient way to explain why an operation has failed. Before the new Solidity error type, there was a way to give that information with the revert function, but that was more expensive in terms of gas because it had to store that additional message in the contract. If you need any random number for whatever reason and you want it to be truly random, use oracles like Chainlink for reasons already explained, and do not use anything else if any important feature or part of logic depends on the number being truly random. Handle refunds. You need to remember that there might be some errors or there might be another reason for a refund to one or more of the majority or even maybe potentially all of the holders. So you need to have a way to do that. Whitelisting, or actually allow listing, is best done with Merkle trees, already explained, and the verification functions for the Merkle hash are available in OpenZeppelin contracts with the Merkle proof. So there's no excuse to not use this. This is the end of part 3 of the episode on how to write a good NFT smart contract. Part 4, the last part of the episode, will be about admin features, tasks to do after the project launch, and the whole section about helpful resources. From good smart contract examples to a learning roadmap if you're just starting out.